Hi, welcome everyone. It's a pleasure to have you all here for the second webinar of our reservoir simulation series, organized by the Chemical Engineering Department of the University of Magallanes, the GeoSeminarios initiative from the GeoLatinas and Argentina student chapter of the SPWLA, the Society of Petrophysics and Well Log Analysis. As you can see on the share screen, we have our promotional flyer, which includes information about the upcoming webinars in this series. On today's slides, we are very pleased to host our speaker, Markus Blatt and Antonella Ritorto, with their presentation titled Open Source Tools, OPM Flow, Opportunities and Limitations from the OPM-OP Europe. Before we begin, let me briefly explain the format of this webinar. The presentation will last around 20 to 30 minutes. During the talk, please feel free to type your comments and questions in the chat, whether you are joining us on Zoom or Facebook Live. After the presentation, we will have a Q&A session. You can write your question in English or Spanish. Our team will be assist in translating them on the speaker preferred language. Okay, continue. Let's introduce our speakers. Our first speaker, Dr. Markus Blatt, is the CNO and co-founder of the OPM-OP and an independent consultant. He has been developing scientific open source software since 2004 as core developer of Dune and later of the Open Porous Media Initiative, OPM. His work includes a key contribution to parallel reservoir simulation, particularly in linear solvers, and the Open Flow Simulator, applied to projects such as a carbon capture and storage, CCS. Dr. Blatt holds a PhD in applied mathematics from Heidelberg University. Next slide, please. Our next speaker, Dr. Antonella Ritorto, earned her PhD in mathematics from the University of Buenos Aires in 2017. She carried out postdoctoral research in the Netherlands and Germany, focusing on variational analysis and anisotropic materials. Since 2022, she has been working as a software developer at the OPM-OP, applying her mathematical expertise to simulation and coding tasks in porous media. Now please join me in welcoming Markus and Antonella. Markus, Antonella, take it away.
Sorry, I was muted. Thank you for the nice introduction, Gonzalo. Can you see my screen?
Yes.
Okay, perfect. Sorry. Okay, so we should start. Thanks for the introduction and for the opportunity to present here. It was very nice also to be here, let's say here, for the first talk, for the opening of Professor Paul Glover, if I remember correctly. And it was a nice opening with this overview of reservoir modeling. So let's try to keep the flow, and what we are going to talk today is about OPM flow. That's, as already was mentioned in the introduction, it's an open source simulator, and I hope that we managed to share with you what we do, at least briefly, and also to mention a few advantages and disadvantages that working with open source can bring. Okay, so as this was done together with Markus Blatt and this talk and the presentation, and we are lucky also to have Michal, other colleague, also in the audience, so we have support for the question moment. Okay, so I forgot to show the time. So to say what OPM flow is, maybe already everyone knows that OPM stands for Open porous media, and here it's a few. There are a few highlights of OPM flow as a simulator evolution. So I'm going to walk through these highlights and just say a few words of each of them. So it all started back then in 2009 as the Open Porous Media Initiative, as a community-driven open source simulator or tool maybe in the beginning, but it ended up in a proper simulator, let's say. And it's a collaboration between these two wonderful worlds, industry and academia. And from the very beginning, compatibility was a key feature, a key ingredient, let's say, because so simulators communicate with the users with input and output files, let's say, or decks, or whatever you want to call them. And being compatible with the industry standards was important, and is still important, and was important from the very beginning. Okay, so the first highlight that we have here is algebraic multigrid. I'm not sure, maybe everyone is familiar already with that, but I shall say a few words. This is a technique that speeds up solving large equations, even on irregular grids, by building coarser levels, and that means, in a briefly way, that we have a bunch of equations with a bunch of unknowns, and we call that fine system, the original system, let's say, or the discretization. And this technique, what it does is to create smaller and simplified problems based on the same equations, and solves that, and then kind of jumps between the fine system and the progressively coarser systems. And in that way, like, the errors are managing kind of more efficiently, and the whole problem becomes more scalable. And this is a nice technique because it's purely based on the linear system, and there is no need of modifying the grid geometrically, let's say. You don't need to glue cells, or you don't need to refine cells. It's pure in the equations. Okay. The next highlight that we have here is the parallelization, and there are a few stars. Like, I guess there was a lot of work going on in parallelization, but we are just choosing to say a few words in these years, let's say. It started in 2013. We have a few highlights in 15, 16, and also nowadays. So MPI-based domain decomposition, what it means, MPI is message passing interface, and is like, to solve larger tasks, let's say, you just divide, you have more than one core, more than one process, and you have some data, you kind of split the task in your processes, and when you need to share data, maybe you don't have to share the whole information, you just need to share a tiny bit of that, and then you communicate with your neighbors, passing a message. And the illustration here, we can think that is representing different stages of the simulation. I don't know, here I have like 4 cores, like each line in horizontal line, let's say. And each process has its local memory. And let's say, I don't know, I parse the input file, then I create my grid, I distribute the grid, the properties, and so on. Then I have some assemble stuff. And in the 4th column, where we see these tiny arrows interacting between processes, is where I need to tell my neighbor some data, so the neighbor can also move forward. And where all these arrows kind of collapse is because at some point we distributed the task, but we want to talk with our colleagues and collect the information. So we need we need a synchronization point, let's say. And then you are ready to write your output file, and then your simulation is done. So this MPI parallel corner point grid and solvers is based on Dune. Dune was mentioned already in the introduction, is distributed unified numerics environment, and that was done by Markus, that he's here. And then we have this parallel asynchronous output done by Robert Klofkorn, sorry for the pronunciation of the last name, from North. Asynchronous means that the processes don't need to wait for each other, and it's like independent, let's say. Okay, the next highlight is automatic differentiation, and this allows the simulation to be to have more accurate and efficient derivatives, and it speeds up the nonlinear solvers. That was in 2018. Something I should mention is there are some references all around the talk, but in the end there are a bunch of links, so don't worry, you will get more details if you want. I mean, not said, but you will get links so you can read later if you are interested. Okay, then in 2019 we started with a commercial usage. So industry partners started using OPM flow for benchmarking and validation, for example, as a black oil simulator. And somehow together with this, no, sorry, I forgot something. Okay, and other highlight in 2019 is related to hardware acceleration. So that was the time where the first version with linear solvers on GPU was done. And nowadays, still there are improvements, and this acceleration process is in progress, let's say. And what this brings to OPM flow is to scale to industry-sized reservoir models on supercomputers. And what I wanted to say together with commercial usage is the need of support and maintenance that was officially set in 2021. So when you start using OPM flow as a simulator, and like industry partners start using that, and then, for example, you notice that you want to run your model and it doesn't work for some reason, the simulation breaks, or your deck has some keyword that is not supported yet. So somehow this commercial usage comes together with support and maintenance, and then we can help and support and maintain all what we do in the simulation, in the simulator. And this is provided by North, OPM-OP, that's so Markus, I, and my colleague and some more, Sintef, and since this year, TNO. TNO is in the Netherlands, North and Sintef in Norway, and OPM-OP is in Germany. We are in Germany. What else? In 2022, we have also this improvement in the preconditioner, the constraint pressure residual with wells, which helps to improve the match of production constraints and pressures. I'm not going to say much about that, not only because it's not my expertise, also for time, so we can move forward to our last highlight of the evolution of OPM flow. There is a recent paper that there is a link later on. Lessons learned in using open source simulation software on real assets model, and this is a nice document, let's say, that shows that OPM flow can handle full-scale industrial problems. So it's used in real assets in production. And in the paper there is a comparison between OPM flow performance or features in comparison with commercial simulators. And yeah, so that's our last highlight. So even though of course, it was used already for industry partners. This is a nice presentation and comparison and with a lot of data. So we added here as a highlight. Okay, and main contributors that in this open source simulator or project. So we have Sintef, NOR, Equinor, OPM-OP, so us, Citron Solution, TNO, Climate, Total Energies, Aero HPC, and Big Data Accelerate. And here is a slide that I'm not going to read, but this is like a summary, not a complete summary of what the simulator does, support, or some features, and so on. So I guess it was clear for everyone that it's an OPM source reservoir simulator that we can use for black oil or CO2 storage. That I didn't mention, but it's one of the things that I would like to say. So from this list, we selected these 3 topics to say just a little bit more. So we start with, so I want to say a few more words about an example of CO2 storage, well management, and custom features like PyAction and Python bindings. So we continue with well management. We have standard wells and multi-summer wells. And as I said, to communicate with the simulator, we need some input file. And in this input file, we have like sections and keywords. And to define standard wells, we need this tool, also for multi-summer wells, well spec and comdat. So for well spec, we have the specification data for the well, like name, group that the well belongs to, etc. And for comp data is the information about how the wells are connected to the reservoir, the connection points. And then the 2 extra keywords that multi-segment well needs are related to the segments. So well seg is how is this geometric cubing shape, let's say, and comp seg is the other keyword that you need to link comp data completion to a particular segment depth interval. And what OPM flow does is to compute the pressure drop and the flow distribution inside this well geometry, well bore geometry. And here there are tiny, not complete examples, just how this section with these keywords would look like for a very simple standard well and very simple multi-summer well. Okay. A few words about PyAction, and for this I would like to thank my former colleague Lisa Neville that I stole this from her talk. And if you click later, if you get the slides of the talk, you can click in PyAction and you will just directly go to the link where her talk is. So with this PyAction, what we can do, we can execute a Python script embedded in the running simulation, which would be this tiny file that we see there. And this is this green and orange. The whole picture is kind of representing the simulation. One step of the simulation, I think. I need to more. And the good thing of having this Python script embedded in the running simulation is that you can access to simulation objects and you can inspect or modify the state of the simulation. And this is similar to ActionX and to what ActionX and user-defined quantities do. And then you can also generate output for post-processing like summary, resin side, and preview. Maybe resin side, I will mention something in a few minutes. A very, very nice idea on how to use this. Of course, it's not detailed, and it's not that after my talk you will sit and just run use your PyAction keyword, but a brief idea on how to use it. To use it, is these 4 steps. So you build OPM flow with this flag on, OPM embedded Python on. You add PyAction in your data file in the schedule section. You create and provide your Python file, and then you run flow. That would be the structure of what to do. And the last thing of these 3 kind of features that I wanted to say a few words is this CO2 storage model, demonstration model at Smehaya. I hope I pronounced it correctly. This was created by Equinor's CO2 storage team, and it's a large model with 9 million active cells, and there is more information there. Per year is injected 15 million tons of CO2 in a vertical well. After 25 years of production, the injection period is 40 years, and then you observe the behavior of the stored injected CO2 after 35 years to predict how safe is the migration and how it moves and so on. And there is also some references there. Okay, that was a bit about like what is OPM flow as a simulator, or what's a few things that are there as features already. Other things I want to mention is, for example, this OPM run, which is our graphical user interface. And the idea of that is to help make easier running simulations with this setup. And you can provide unified interface for a bunch of cases, let's say. And this is a screenshot of how it looks like. And it might need some improvements, but it's still a tool that we have to make things easier, hopefully. Then we have ResInsight, the visualization tool is also open source. Here we have a nice screenshot where you can see you can select a lot of properties, you see the grid, you can plot stuff, compare results. So it's not only just to visualize the output of your simulation, you can do a bunch of things to compare data and plot stuff and so on. Okay, so then, as the title promised, we also want to mention advantages and disadvantages of working with open source tools, in particular with OPM flow. So advantages might be clear by now, but just to mention, it's accessible, so it's open, so it's free, no license, and that's transparency, of course, is open, so you can go and read the code if you want, understand the algorithms that are there. And compatibility was mentioned already in the beginning, so reads many industry decks, and we have a community, so we meet regularly, maybe once a year, or maybe more, but we meet as a community. We are always communicating and yeah, in the website that will appear in a few minutes, you can also find talks and we present in conferences and so on. So we are an active community. And we have an OPM reference manual that is user-focused, that I will say a few words soon. So I just leave it like there in the list of the advantages. And limitations, of course, we are not perfect, we are all human. And one first limitation is that, of course, not every single feature that you want or is needed is there implemented already. So we implement by need. Anyway, so we have there is constant effort of extending the physics models. For example, compositional PVT, so pressure, volume, and temperature models, and geomechanics. For example, they are in a steady progress. And the learning curve can be steep, but if you look closer, there are a bunch of opportunities for research. I don't know, improving the numerics, adding machine learning, improving performance. You can find always room for improvement. Maybe getting started is not as flat and soft as you expect maybe, but there are opportunities there. And the simulator itself is Linux. Well, it's a Linux with my Argentinian accent. I don't know if it's Linux in English. Well, Linux and command line centric. But this can be overcome by using Windows subsystem for Linux or OPM-RUN, which is this graphical user interface that we have. So this is just to share with you. Of course, we have nice things and a few things that they can enter in the limitations category, let's say. Okay. If you want to get started with OPM Flow, you can take a look at the website, for example, and there's a bunch of things, the documentation, talks, the manual you can find there, resin site. If you don't have your own tests yet, you can also use tests that are there, datasets, a lot of things. As I mentioned, there is also the reference manual, which is a huge document, so don't dare to print it. It's just for consulting when you are looking for a keyword and you don't know if it's supported or not, or you don't know how to write the section of that keyword in your input deck, or you need some command line instructions, or you want to read a bit about the methods. So it's user-focused and it's always being extended and updated. And then, of course, you need to install OPM Flow. You can check in the website if your platform is listed there, or otherwise contact us if you have any problems installing OPM Flow. The recommendation is to use binary packages, and there is here the instruction. And then after this, you are ready to try your first case, to run your first case. Okay, and to summarize a bit, one of the takeaways that we would like to share is, of course, commercial simulations are also there. It's not that OPM Flow is the only and unique simulator you can use in your life. Of course not. But if we compare with commercial simulators, of course, they imply high cost. They are kind of a black box, and okay, run your case, your case doesn't work. Well, you cannot really investigate what's going on because it's not transparent, let's say. And in the case of parallel runs, you might even need multiple or special licenses, which implies like higher cost also. And this is a barrier for students, researchers, and consultants. So OPM Flow is an open source alternative for reservoir simulation, accessible, transparent, research friendly, hopefully, and it was proved that is used in real asset models in production in black oil and carbon capture and storage. So this is our takeaway, and I hope you run your first OPM Flow case. It's free and only an instruction away. So thank you very much for your attention. And what I promised, a bunch of links. So if you want to go deeper into who we are, OPM-OP, there is our website there, the project website, the documentation, the reference manual, the graphical user interface, OPM-RUN, visualization tools, and then kind of all the topics that I mentioned, including also Dune in the end. So the links are there for going deeper. Thank you very much.
Thank you so much, Antonella. This was such a great presentation, and I hope it's useful information for everyone that has joined us today. We do have a question on the chat, and it says, how flexible is OPM flow in extending to EOR, enhanced oil recovery processes such as CO2 injection, polymer flooding, or solvent models? Can you give any details related to the Equinor case study?
I would like to handle the question to the most experienced person I know, Markus Blatt.
Yeah, so maybe I can answer that. Yeah. So I think OPM flow supports CO2 injection. We also have, I mean, it's not like one simulator, basically. It's several simulators under kind of an umbrella simulator. And we do support CO2 injection. We do support polymer flooding and solvent models. So I think one of the main goals when this project started was actually enhanced oil recovery. I hope that answers the question.
Yep, thank you so much. I hope that's clear for people that are watching this. Another question that we have is, what challenges have you encountered with the Eclipse deck parsing and compatibility?
Okay, maybe I can answer that too. Oh, many. I mean, I know a former colleague within OPM-IS, he did most of the work or much of the work in Eclipse deck parsing and compatibility. And I mean, it's basically a black box, right? So you have these keywords and then you try to implement them. I think the parsing is actually the easy part. I think the hard part is actually how the simulator reacts to these keywords. But I think we managed to quite some extent to be compatible with Eclipse. So this was one of our main focuses.
Okay, let me check if we have questions over Facebook. We don't have questions there, but I do have a question. Is like, could you give either Antonella or Markus, could you please give us an example of what one of the main outputs will look like? What a user of the interface will expect to get once they use OPM?
Well, I think the users mainly expect to get similar output as with other black hole simulators. So I mean, usually what you do is like it was enlightened in the previous talk, you do some history matching first to adapt the simulator to the actual behavior of the reservoir, and then you try to predict the future based on that. So the expectation is, of course, that you get some good numbers about how much oil you can recover from the reservoir, or in the case of CO2 injection, how the CO2 inside the reservoir will behave and where it will go to, and such things.
Okay. We have one last question. It says, how do you envision the future role of open source simulators in digital twin or real-time reservoir management?
Oh, that's an interesting question. Yeah, we hope that an open source simulator can be used to to allow such things because of the nice license that you have. So you can just use it. So I think for the digital twin, it's quite an advantage for real-time weather management. I don't think we are there yet. Currently, these weather simulations take a long time. I think if you want to do that, then you need to produce some simpler models. I mean, what people are doing now, or working on, is to have like a weather simulation running and then see how it goes, and try to change it during the simulation or restart simulation very early. But that's something that we are working on currently.
I see that. A personal comment is I really like that OPM has this extensive manual. I think that's a differentiator from other open source tools that are around there. Sometimes you have the tools, but if the user doesn't know how to use them and it's not accessible, it actually hinders the possibility of more people using it. So I really appreciate that the developers have taken the time to do this. So thank you so much for the talk, and thank you so much for the work that you're putting into creating this open source software and helping into getting more students and more people to learn about what can be done in the industry.
Thank you for the opportunity to present.
Yeah.
And now I think here, Danita, you want to take over to make the recognition to the presenters?
Sure, thank you, Valeria. So please, Markus and Antonella, receive this token of appreciation for your time for this talk, and be present with this webinar series in reservoir simulation that we are very proud in the Global South to make this happen with GeoLatinas and the Argentine student chapter of the WLA and the Universidad de Magallanes. And for myself, personally, I'm very grateful of you too, of your company, because actually you've been helping me a lot with my research project and my students to start learning in baby steps using the software. And so thank you for everything. And I think I will finish again, I guess. So here are the social media of all the organizations that are part of this webinar series that you can just follow. Yes, Instagram, LinkedIn, Facebook. The recording of this talk will be available on GeoLatinas YouTube channel probably next week. By the end of the week, the first talk poll will be uploaded, and you just you can just follow us. So, and finally, we're just going to return to the webinars flyer. We have 2 more talks coming next week. There's one talk in Spanish with Martín Verdugo from the Chilean oil company. He's going to give a talk about personalized type curves to assist production, forecast, and history matching. And the last talk will be in the last Thursday of the month about the Universidad de Magallanes project in reservoir simulation. And by the end of that talk, a manual of tutorials in Spanish will be released to the young professionals that want to start navigating and learning reservoir simulation using open source software of OPM-OP. So again, thank you so much, Antonella and Markus, for attending and accepting to be the speakers of this talk. And thank you to the audience, whether you are in Facebook Live or in Zoom. So yeah, I don't know, you want to say a few words, Antonella and Markus?
I just want also to thank again the opportunity of presenting here, and I enjoyed to be part of this, and it's a very nice nice event, and yeah. And then I can share the slides. I don't know if they appear somewhere, but the links for going in deeper in the topics are there. So I will send it by email, and I don't know if someone wants our emails are also there. If someone wants to contact us, no problem.
Yes, certainly. And we can share the presentation with the people that is registered. So for those watching this talk, there's a QR code that you can scan and you can just register, and we can just share the slides with this talk. So no worries about that, Antonella. Thank you. Okay. Cool. Okay, so I think that's a wrap. Thank you again for staying tuned in GeoSeminars from GeoLatinas initiatives. And let's see you next Friday. Have a nice day, everyone. Bye-bye.
Ciao, thank you.
Thank you.